All right, welcome back after lunch. My name is Beck Dalton from the US EPA, and our co-chair is Noel Diet from USGS. And today's session is new tools to communicate air quality and atmospheric deposition results. And we're going to start off with our first presenter, Denny Murray from University of New Hampshire.
Hello, everyone. I'm Denny. I'm a PhD candidate at University of New Hampshire, where I study trends of wet deposition and composition through the lens of global climate change. As my talk title probably gives away, I am particularly interested in the organic nitrogen fraction of wet deposition. And so I'm excited to be part of this session on new tools to show you some of the things that I've leveraged throughout my PhD, and also share a case study with you that Mike Bell and I have been working on to understand how much organic nitrogen may or may not be influencing critical load exceedances across the US. So organic nitrogen is part of the atmosphere terrestrial exchange of nitrogen and carbon through landscape sources like industrial combustion processes, biomass burning, marine emissions, plant emissions, and agriculture. And these emissions can directly emit organic volatiles into the atmosphere, and then they can become nitrogen containing through transformations. And those gases and aerosols are then dissolved into precipitation and deposited back into the Earth's surface via wet deposition. So this is very similar to our inorganic nitrogen cycle, but I just want to remind you that the same processes apply here. Once on the landscape, the dissolved organic matter fraction plays a huge role in biogeochemical cycling of nitrogen between the exchange between biomass and inorganic nitrogen. And I just want to remind you too that the organic matter pool is basically any sort of carbon-based molecule, and organic nitrogen is part of that organic matter pool. So it's really this catch-all term that we use to classify any sort of carbon-based molecule with a nitrogen-containing group on it. So as I mentioned, it's part of DON encompasses a lot of different types of molecules, and we actually don't currently have a lot of direct ways that we measure DON. We mostly calculate DON as the difference between total dissolved nitrogen and dissolved inorganic nitrogen. So I'm going to refer to those as DON, dissolved organic nitrogen, and DIN, dissolved inorganic, throughout the talk. And I'm showing you here a ternary diagram because these are in a relative abundance space. So you have the percentage of ammonium, nitrate, and DON on each of these axes, and each of those dots is reflective of the percent contribution of each of those within that total dissolved nitrogen pool. We don't really measure TDN or total pool, and therefore DON is very rarely measured throughout the US. Some places in Europe are doing this. But where we are measuring it, and at one of those locations is in New Hampshire, where I do a lot of my dissertation research, we are finding that concentrations, relative abundances, and loads are increasing over time at a pretty remarkable rate. I think that this is very well displayed by this ternary diagram, where you can see the colors of those dots are shifting downwards towards that bottom corner of DON from 2004 when we started monitoring to 2020. And of course, this data is continuing today. I'm just showing you till 2020. But I just want to remind you that this is a calculated variable. And so our analytical precision has kind of held us back in the past from measuring DON because it's dependent on how well we can measure inorganic and total dissolved. But I think we're in an age where we've sort of grappled with those challenges, and we have been seeing the DON showing up more commonly in the literature here and there. So in some meta-analyses, we found that organic nitrogen in wet deposition can comprise on average 30% of that total dissolved nitrogen pool, and even up to 92% in some cases. So this is a significant amount of nitrogen that's coming into our system and remains largely unquantified. We also know that DON is likely just as bioavailable as inorganic nitrogen, and therefore may impact ecosystems to the same degree, right? So we know that, for example, experimentally, wet deposition DON can stimulate the growth of marine algae and bacteria to the same degree as inorganic N. And this is probably because our organic nitrogen pool is comprised predominantly of amino acids, which are highly bioavailable. And they're highly bioavailable to organisms that we use as indicator species for how nitrogen deposition is impacting ecosystems like lichens. So this is an important component of deposition. So right now, one of those ways that we consider how nitrogen deposition is impacting ecosystems is through critical loads. So if you haven't heard of critical loads, there's a whole session on it tomorrow, but we're going to get a sneak preview now. But critical loads are a key metric for understanding how ecosystems respond to excess nutrient deposition. And we have, as the literature has sort of developed these critical load thresholds, which is basically this deposition concentration of a given nutrient below which specified harmful ecological effects do not occur, right? So when you do have deposition exceeding a critical load threshold, it can lead to changes in biogeochemical cycles on land and water, vegetation tissue changes, declines in growth and mortality, and shifts in community composition. And the trends and rates of those can change depending on how much or how little nitrogen you have and the ecosystem response that you have as well. So one of the goals with applying critical load thresholds is just determining where and when they are exceeded, because there are some pretty significant management implications. Right now, this is largely done through maps of total nitrogen deposition that are made by the NADP and EPA. So these maps include wet and dry inorganic nitrogen deposition, as well as estimates of unmeasured species. So here I want to remind you that that total N is really just the sum of ammonium and nitrate. We are not measuring total dissolved nitrogen here, and therefore we're not measuring organic nitrogen. So, I think I'm probably driving this point home. We are missing a component of the nitrogen cycle. And so Mike and I met at AGU last year and connected about trying to involve organic nitrogen into critical load exceedance maps. And we're sort of conducting a small case study. This is all preliminary results for how we want to potentially start thinking about organic nitrogen in this concept. So the goal of this was to use archive samples from the NADP to hindcast concentrations of organic nitrogen, and we're going to incorporate those organic nitrogen estimates into our critical load exceedance maps. And this is going to be an outcome of sort of a first order approximation of how much this very often unmeasured component of nitrogen wet deposition is influencing ecosystems. So first, I'm going to briefly explain how we were able to even quantify DON in wet deposition samples. So through the NADP archive sample program, I was able to get over 300 samples that represented 17 sites that were collected in 2017 and 2018. Here's a map showing each of these sites and the level 3 ecoregion that the sites fall under. So as I mentioned, these are archive samples, right? So in order to ensure that these samples were stable, we actually went ahead and just reanalyzed some of the solutes that NADP has measured in the first place. So we're taking concentrations of nitrate and ammonium N, so just that N fraction, that I measured at UNH, and I'm comparing directly to the concentration of N that was measured by the NADP. And you can see here that we have a pretty strong relationship for about 92% of our samples. We considered our samples unvalid if they fell within that, they fell above a 10% error threshold, which is a common analytical threshold. And so for the samples that fell within those all those dashed lines, which is about 284, we were able to calculate a new measurement with more confidence, right? So now we can measure total dissolved nitrogen, and if we also have our inorganic nitrogen, we can get at DON. I'm not going to go into the details of how we did all this, but this was very recently published last week in JGRB, so urge you to read that or ask me questions later if you want to learn more about how we did that. But the case study here is using that DON data set of 284 samples that again represents samples collected in 2017 and 2018 from just 17 sites. And then we're going to apply these DON estimates to these critical load exceedance maps. So we're going to walk through some math here. And we'll mention this is sort of Mike and I's first pass at this calculation. If this inspires any other ideas on how you would do this, I please would welcome that discussion because we definitely went back and forth on what the best way to do this was. But what we decided on was for each measurement in site, we're going to calculate the proportion of annual precipitation within the sampling period. And we're going to multiply this by our percent DON in the sample. So we're working in percent space here as denoted by the ternary diagram and the equation on the top. And then what we're going to do is we're going to sum all those weighted percentiles to create this precipitation weighted scalar value for wet deposition N. And we're going to apply this scalar value to the appropriate level 3 ecoregion that's displayed in the map here. And so we have both spatial and temporal variability. Our DON scalar is going to range from 1.3% to 15.5% depending on the ecoregion and the year. So for each year, we're going to take that DON scalar value, right? In 2017, 2018, we see some spatial differences, and we're going to multiply that by our total deposition within that flux that happened within that cell within that year. And that's going to give us a conservative estimate of our TDEP when considering DON. So we have basically two data sets that we're comparing here. Our first is our total deposition, business as usual, assuming that TN is equal to DIN, right? And then we're going to have our sort of new data set, which is our total deposition multiplied by that DON scalar value. So also considering that extra input that's relative to precipitation. So we're going to compare those maps to two critical load thresholds. The first is lichens, and this is representative of our sensitive ecosystems at 3.1 kilogram N per hectare per year, and also our herbaceous species, and this is representative of our resilient ecosystems at 6.1 to 27. I'm also going to mention that these critical load thresholds are derived only based on known relationships with inorganic nitrogen, so there's already bias baked into that, but we're going to move forward anyways and see what these maps look like. So I'm just going to walk you through interpreting these critical load exceedance maps with DON inputs. These maps are pixel based. So each of these pixel colors, the color is going to be the same throughout the map. So I just want to make sure everyone's on the same page with interpreting these. Any gray area is a cell that is already exceeding a critical load threshold without considering that DON scalar. So DIN alone is pushing that cell above our critical load threshold. But any red areas are actually new areas that are now in exceedance when we consider that DON threshold. So multiplying our TDEP by that DON is pushing that ecosystem above a threshold that is now causing it to be in exceedance of a relative critical load. So here's a map for lichen exceedance. As you can see, there's not a lot of red in this map, which really just means that we're above 3.1 in most places with DIN alone. So there was about a less than 1% increase in total area exceeding our critical load N when considering our DON inputs. But this 1% was not necessarily evenly distributed. I want to point out some specific results to Class 1 lands, which are large national parks and wilderness areas. And as per the Clean Air Act, have special air quality regulations, and this includes management for nitrogen deposition. So we went ahead and looked at what was going on in these Class 1 lands, and we see that when we do just consider those Class 1 lands and DON, there's an increase in the area of exceedance in 13% of our represented Class 1 lands. So even though we maybe have a national wide of only 1%, it is relatively affecting our Class 1 lands more. And sorry, this is Yellowstone National Park. So again, there is temporal variability. So that top row, 2017, you only see the new red cells sort of on the top of the graph there. But in 2018, you do see large parcels of land increasing the area of exceedance within Yellowstone National Park. So next I'm going to show you the herbaceous species richness exceedance maps with DON. So again, this is a different threshold, right? So we're having a different set of gray cells here that we're considering compared to lichens. But here we saw about an 7.4 to 8.8% increase in total area exceeding. So we have more cells that were right on the cusp of exceeding. And then when we added that DON scalar in, it was pushed above there. And then again, if we were to zoom in on those Class 1 areas, we see only an increase in 6% of our represented Class 1 areas. So maybe that particular resiliency threshold isn't as important as lichens, but I want to point out sort of the top row in 2017, you're almost doubling your area from gray to red there. So this is an important component of this analysis, is sort of zooming in on certain areas. So I'm just going to sort of breeze over some takeaways. So incorporating DON to total deposition estimates, very first pass, very preliminary, does seem to push ecosystems over previously unviolated critical load thresholds. But these are conservative estimates. For example, I did not have a continuous year of DON data. These are only probably about like weekly samples that we've sort of extrapolated to a year. And so an annual contribution of DON is likely much higher than what is displayed here. We also only have 2 years of data. So just some grains of salt to be taken. Nonetheless, despite those caveats, we can probably understand that DON's increasing, and it's also at magnitudes that can impact ecosystems. And this may extend the recovery time of ecosystems given excess N loading. And it's also important to consider that our DON magnitudes are not equal spatially or temporally. We find that concentrations are very high during the summer, which is also when ecosystems are going to be the most primed to be taking up nitrogen. And we also find that our DON loads vary spatially. So I urge you to look at this paper if you're more interested in those results. And then, of course, there's so many questions about where DON is coming from, what are its sources, what is it made of. What we do know is that the seasonality corresponds with the growing season. There are biogenic sources of DON that go up into the atmosphere, and many of them are linked to climate change. So there's a lot of remaining questions here about whether or not DON will become more important in the future. But in the spirit of this session, I want to end my talk with some lessons learned. some future directions, and some new tools that I think are a promising way forward for incorporating DON into wet deposition studies. First, biasly, I think archive samples are one option for getting at a conservative estimate for hindcasting DON or even other unmeasured solutes, including DOC. And estimates of DON rate, I'm only considering wet deposition here, but certainly there is DON in dry deposition. Can reference some of Janice Brainey's work here. But ultimately, it would be great if we could develop some sort of measurement model fusion to include DON in TDEP. And one way that I know NADP is pursuing this is through the snippet samplers, so keep up that. And I think some of my own research interests lie more in the molecular classifications. So what is DON made of? Is it amino acid based? Is it more recalcitrant? And I think those methods like FTI-CRMS could be a promising way forward, as well as relating that to DON bioavailability experiments, specifically with lichens. With that, I will take any questions, and I want to thank people at the NADP, David, Amy, and Brett, as well as my co-authors and my collaborators at UNH. Thanks.
We have about 5 minutes left for questions.
Thanks. It's really interesting to think about the ways that DON might influence and the kind of complexity of trying to adapt the critical load system. I think I missed at the beginning. I know you talked about a lot about percent that DON represents, but is DON, the mass of DON actually increasing? Because of course the DIN is decreasing so much, so it could be staying the same. And
Sure. Yeah, that's a good question. I only showed you relative abundance graphs, but where DON is measured long-term, I will say there's about like 5 places in the world that this is measured for longer than a year. We do find both concentration, load, and relative abundance are increasing. So yes.
And then the other thing is just thinking about like some of the analyses that we do and whether it's a reasonable assumption that the ecosystems are going to respond the same way to, first, are they going to respond the same way to DON as they're responding to DIN, but also, thinking about some of the analyses that we've done, and, you kind of would have to go back and see whether, in the easy way, whether you could explain some of the variability with the DON difference, or you'd have to redo the whole analysis.
Absolutely. I think you're touching on a couple points. If you missed the beginning, I'm just going to show you a quick slide because there are some studies. Sorry, this is probably very dizzying for people. There are studies that have measured that DON is just as bioavailable as inorganic nitrogen. So in terms of the first part of that question, I think yes. I think what we know, this is a huge field to be explored, but I think what we know is that in some cases, it is just as bioavailable and therefore could have the same ecosystem impacts. What I didn't mention in this study, and I'm hoping Sarah Lance is here somewhere, is that DOC and DON are also disproportionately contributing to organic acid contribution in ecosystems too. So you have a whole acidification sort of side story to this as well. And then to your point about going back, yeah, obviously we can't do that, but I think there's ways that we could potentially incorporate this into models in the future for sure. And I'd love to chat more.
A question or 2 comments for you. One, I don't think I heard you say it, but you're measuring the organic nitrogen from the NADP samples, which are not preserved to maintain the organic nitrogen. So we know that there's going to be loss. So this is really a lower bound on the organic nitrogen, and your concentrations are kind of representative of that because they're pretty low. Most are less than 10%, but often there's more than that. But the other point, and the point of your talk here, and I'm really glad you put it up, is that what do you compare to the critical loads? And simply incorporating the organic nitrogen, I think is really important. But how are those critical loads developed?
Yeah,
Were they developed with an organic nitrogen fraction in them? And I kind of think no, although
no, they were not.
you'd be able to tell us more.
Probably not.
But We've actually been thinking about this in our own work because not only are we missing organic nitrogen, NOx, and these other contributors to the total nitrogen, but how do you handle something like ammonia dry deposition, which is bidirectional? In fact, there's other nitrogen compounds that are bidirectional, meaning that the ecosystem is losing them as well as it's being deposited. And so do you look at a net deposition or do you look at just a downward deposition flux? And what do you compare that to actually when it comes to the critical load? I think it's a really important and significant question because a lot of these processes are nonlinear. So we just simply can't assume that if we develop the critical load based upon inorganic nitrogen, that that's all we need.
Yeah.
So good work. Thank you.
Thank you, Brett. Yeah, I want to definitely echo the last part of your comment about ins and outs, that DON is a VOC. So, we're losing these types of compounds from ecosystems as well. But whether or not that translates to how we sort of frame critical loads and the empirical models that we use to get at that, I think would be a really interesting question. So definitely one to ponder.
Great. Thank you so much. Okay, next up, we have Karen Elizabeth Martinez Ozejo from Agency for Environmental Assessment and Enforcement. Will be giving a virtual presentation.
The influence of ventilation index on sulfur dioxide deposition in a mining metallurgical area and its effects on coastal hill vegetation in Lima, Peru. This research was conducted to better understand the impacts of sulfur dioxide emission from industrial activities on local air quality and the surrounding vegetation. Let's begin with an overview of the study and our key findings. Here is an overview of our presentation. We will begin with an introduction to our team and the background of this study. Then we will cover the objectives and we aim to achieve, followed by the methods used to collect and analyze data. After that, we will present our results and finally conclude with the main takeaways from our research. Our team consists of specialists in environmental engineering and botany, each with unique expertise in geology, meteorology, air quality, and botany. Together, we bring a comprehensive approach to studying environmental impacts. We are currently master students and environmental evaluators at Environmental Assessment and Enforcement Agency of Peru. The Environmental Assessment and Enforcement Agency, Peru, in the context of its functions, conducted a study in a coastal industrial area where a metal refinery operates, aimed at determining the effects of SO2 emission of air quality and coastal hill vegetation in an area affected by industrial activity. In this study, we examined the atmospheric ventilation index, a key metric that helps us assess the atmosphere capacity to disperse pollutants. The ventilation index is calculated based on the average wind speed and the heat of the mixing layer. Higher values indicate good ventilation condition, allowing pollutants to disperse more effectively, whereas lower values suggest poor dispersion conditions. This slide presents the source of acidity and their effects on plants, focusing in the impact of acid rain. Key effects include damage on the cuticle due to direct acid action, cellular damage from acid penetration, and interference with stomatal functioning. Additionally, there is an observed nutrient imbalance, leading to deficiency in phosphorus, calcium, magnesium, and molybdenum, caused by higher levels of toxic aluminum. Lastly, acid rain also interferes with plant reproduction. The objective of this study is to assess the influence of the indirect ventilation and SO2 emission on air quality and tillandsial species with the industrial impact zone. By examining the parameters, we aim to include the extent to atmospheric dispersion and sulfur dioxide generation affect both ambient air quality and the health of tillandsial communities with a particular sensitive of air pollutant. Sulfur dioxide in the atmosphere converts to sulfuric acid, which falls in the ground and dissociates into sulfate, forming gypsum, or soluble salts. The figure shows the conceptual model with the emission source, transport routes, and receptor evaluated. In this part of our methodology, we conducted SO2 measurement using thermo model 43i and automatic ultraviolet fluorescence analyzer. This equipment was complemented with meteorological measurements, including wind speed and direction, humidity, temperature, and pressure. We collected data at 5 locations positioned both upwind and downwind of the industrial activity area over a span of approximately 20 days. For this study, we determined the atmospheric ventilation index, which helped us understand the atmosphere capacity to disperse pollutants. The ventilation index was calculated using variables such as the height of the mixing layer and the average wind speed between the surface and this layer. These variables were obtained through modeling with the Weather Research and Forecasting Model, WRF. On the left graph, you can see the hourly variation of the ventilation index, showing higher values during midday when dispersion conditions are generally better. The graph on the right illustrates the monthly variation with peaks in certain months, indicating seasonal change in dispersion capacity. Additionally, in early hours of the morning, it is observed that the ventilation index is very low, preventing the pollutant emitted during this hour from dispersing easily, which increases the concentration of the atmospheric pollutant and receptor near the source. We analyzed the sulfur content in plant tissue of tillandsia, specifically Tillandsia purpurea and other tillandsia species. Using the ICP-MS method, we collected 19 samples from the precious leaves within an area up to 5 square meters. This approach enabled us to quantify the sulfur levels present in these sensitive plants. Additionally, we performed a statistical analysis using the non-parametric Kruskal-Wallis test to evaluate the data distribution and difference between the samples. The sulfide dioxide concentration recorded at the monitoring point, CA1, CA3 upwind, and CA2 downwind during the monitoring period from April 26 to May 17, 2021, exceed the air quality standard of Peru of 20 micrograms per cubic meter. It is important to note that SO2 concentration at the downwind point, CA2, were higher than those of the upwind point, CA1 and CA3, as shown in the figure. Increases in sulfide dioxide at the downwind point, CA2, between 12 a.m. and 6 a.m. were recorded to 1 to 4 hours after increases at the source point, CA4 and CA5, due to calm wind and low ventilation index values. The ventilation index and the natural barrier of Cerro Grande keeps the SO2 over the refinery until after 6 a.m. when wind speed above gradually push the gas downwind. In soils, a material was observed covering the soil, specifically over horizon A and AC, along with rock fragments and the tillandsia population. This material formed a loose, powdery, and spongy layer, which is characteristic of soil with sulfate and salts. Then the entry of sulfur in plants primarily occurs through the absorption of sulfite or sulfite from the soil via the roots. In the case of tillandsia, which have a reduced root system, absorption happens through trichomes or leaf scales, in addition to direct uptake of SO2 from the atmosphere through the stomata. Inside the plant, these molecules are primarily reduced to sulfite. The concentration of sulfite in the tissue of 2 species of tillandsia was evaluated. During sampling, it was observed that the tillandsia population in Cerro Grande sector downwind were dead, whereas leaf individuals could still be found in upwind area. The analysis of sulfide context showed that the concentration in the plants from the downwind area were significantly higher compared to from the upwind area, supported by the Kruskal-Wallis test. The highest concentration observed in the area exposed to SO2 emission are intensified by very poor ventilation index, which difficult the dispersion of these gases. It is concluded that SO2 emission from the refinery have significantly influenced to the decline of the tillandsian population in the surrounding hills. While a generalized decline in population is observed through the study area, a greater deterioration in the community of tillandsia present in the downwind zone was noted. Among the reasons that may explain the increasing mortality of the tillandsian community, alteration in plant nutrition can be mentioned. SO2 directly influences changes in plant nutrition that are related to accumulation of sulfates and their derivatives. In addition, the acidification produced by the oxidation of sulfur dioxide, which negatively affects plant development. Furthermore, studies have demonstrated that higher sulfur accumulation within the plants can increase the toxic effect of certain metals such as zinc. To conclude, influence on the environment, the concentration of sulfur dioxide generated by the refinery affect the air quality over the downwind area, CA2, especially in the early hours of the morning from 12 a.m. to 9 a.m., a period during which low ventilation index and calm conditions occur, accumulating SO2 emission in the vicinity of the refinery. Concentration downwind increases due to the influence of refinery emission during periods of calm, poor ventilation index, and extreme SO2 concentration events. The influence of other anthropogenic activities located upwind of the refinery was ruled out, and it was evidenced that the upwind points SO2 concentration were lower compared to the source points and downwind throughout the entire evaluating period. On the tillandsian communities, species of the genus Tillandsia were good indicators of atmospheric pollution because of the absorption of SO2 occurs primarily through the left surface. From the result of sulfur concentration in the plant tissue of Tillandsia, there was a statistically significant difference, with higher concentration in sample collected from the upwind area, showing a maximum concentration of 16 milligrams per kilograms, in contrast to 3 milligrams per kilograms found in the sample obtained from the upwind area. This demonstrated that greater atmospheric pollution toward the north and northwest of the refinery. The environmental effect of the tillandsian community included higher mortality rates of species in addition to increased concentration of sulfur. And finally, we review this bibliography. Thanks.
Okay. Up next, we have Yong Liu from the USDA Forest Service.
Hi, everyone. Yeah, I'm going to present a proposed project to develop some tools to improve estimate of smoke deposition. So this proposed project was developed by a team from universities and federal agencies, including Forest Service, NASA, and the EPA. And one of the collaborators, David, is sitting over there. So, yeah. Okay. Okay. So wildfire has increased dramatically in the United States. So from here you can see on the left is a total burn area. So in the past about 70 years, in the first half, the average annual burn area is about 1 million acres. But see that in the second half increased to about 3 to 4 million acres. So one of the reasons is the increased size of individual fires. So basically in the beginning of about 30 years, which is the like a time period for climate average. The average size is about 1,000 acres, then increased to like 2,000 acres in next 30 years. Then in recent about a decade, it's even increased to like 3,500,000. So a lot of research has indicated there is some contribution from and through the climate change. So fire emission, so you see the list on the left, there's a lot of emissions of air pollutant in both like gas and particle. So besides carbon, I mean CO2 largest emissions are like PM 2.5, which like have a lot of like air quality and human health impact. Also nitrogen and sulfate compounds. And so in terms of the contribution to total total emissions, you see the fire emission in continental United States contribute to about more than 1/4 of total PM emissions based on EPA data. Also, there's emissions of ozone precursor from fire. So if there's a 5%, then there's like more than about 15% chance that the ozone created by fire will exceed the EPA standard. So after emission from fire getting into the atmosphere, there's a long-term and long-distance transport by wind across region, even close to continents. Then there is a deposition of these particles and the gases in the air. They affect the ground, soil, water, and these kind of things. So here you can see a lot of research indicate the larger deposition of smoke emissions. On the left is from the Superior National Forest, just north of this town, which shows like about 2 weeks after a fire, the molecular deposition is about 3 times of the level before the fire. And this kind of larger deposition can last months, even longer. Also, during last year in Canada fire, there is a measurement in watershed in New York State. So there is several smoke events, basically 3 of them. Then two of them came with rainfall. So the measurement in the water shows a big increase in fire deposition. Then this fire deposition can contribute to the total deposition. So this has a larger spatial variability. So basically, absolute values is larger in the eastern United States, also in the west coast, also the North Rocky Mountain regions. Then in terms of ratio or the contribution to total deposition, the largest is in the west United States area, northwest actually. So basically, for the hydrogen and the sulfate, the range for annual average is about around 10%. So this kind of fire, one more thing. So this is the annual average, but for specific fire season and a specific location, like in California, this ratio can be more than like 50%. Then this will like have some impact on ecosystem. So here for the California for 2020, left is without the fire deposition, right is with smoke deposition. So we see the area with the deposition exceeding the load is much higher. if there's a fire emission. Okay, so NADP has been working on different focus area like mercury, acid rain, and nitrogen sinks. Now, with the increased fire and the increased fire emission impact, smoke deposition may be is another new focus for NADP, especially because the increased fire is affected by climate change. So we expect for a long time period this issue will exist. Actually, there is some effort going on. Like yesterday, when we had a TDEP subcommittee meeting, and there are at least 2 research were related to fire issues. So one is there is a smoke tracer analysis for the wet deposition. This is leading by EPA. Then there's another tool developed by Canada, which is pretty similar to the tool from the United States, but it covers a larger area, including Canada, United States, and cases North Mexico as well. So that system actually includes some fire processes. For this, we are thinking this issue as well. So for this presentation, basically we talk 2 things. First, we are thinking about to develop some tools based on current TDEP measurement and model fusion method to include the fire smoke deposition. Certainly, there's some issues which is different between fire and other deposition. So we are looking to these issues, and some issues we have to do some research to understand and to improve. So we start to working on some of these issues. So the second part of this presentation is to present some preliminary results on one of the issues, which is the feedback of smoke on the atmosphere, which to see how this feedback and the changing the atmosphere can affect modeling of smoke deposition. Okay, so left is the how the TDEP method to produce the map on the right. So basically for wet deposition, there is NADP stations to measure the concentration. There is recipient data from PRIMS model. So this creates the wet deposition. Then for dry, there is a ground measured concentration. Then from CMAC, the EPA regional air quality model will simulate the atmospheric velocity, so combined to produce a dry deposition. So for smoker, there's something special which you have to deal with. So first is the resolution and the frequency of the network data. So basically for current networking data, it's like a weekly or around. Some are more frequent, but smoke is more dynamic. So you can see the smoke plume like change from day to day or from month to month. Also, the smoke is individual event, so it has a larger spatial variability. So current NADP network may miss some important spatial and temporal variability of smoke processes. Then the solution, possible solution, number one, so different from like current practice for TDEP heavily based on the data from networking. So we try to get information from satellite remote sensing. So there's a bunch of satellite products we can use. One of them, which is pretty new, launched last year, which is Tempo. It's a special product for air quality. So this year in February, we had a field measurement of pressurized Boeing in Fort Stewart military base in southeast Georgia. So we used, you see the plume on the left, then the Tempo products on the right. You see the Tempo basically can catch the spatial structure of this plume. So this is a direction we try to address the resolution issue. Then smoke has a lot of complex process in the atmosphere. And number one is emissions. So this is a big uncertainty area for smoke simulation and the air quality impact. Then there's the plume rise. So unlike like an area source, it's a point source. You have to determine, decide how high the plume can go. So that will determine its local or long distance regional smoke impact. Certainly, a smoke plume is very dynamic. You see on the in the bottom there is data from weekend field measurement. So it shows the change with time even over a period of 6 hours for the nitrogen species. So we have to understand that this, try to improve the model in simulation this complex processes. So one good thing is in recent years, there are several big field measurements, which is very comprehensive from ground field conditions, fire behavior, and atmosphere process, also the smoke. So there's like FIREX, ECHO, and NASA and NOAA leading that. We can is an NSF funded project. Also there's a FASME, which Forest Service is leading. So we have some data, and then use this data we can evaluate and try to improve the modeling of smoke processes. And currently, we know the concentration of fire smoke deposition to total deposition, but this evaluation basically is for like a certain short period, a year or several years. Then for the specific geographic research, geographic regions. But if you look at the bottom, so for the blue part, which is like a background deposition, is very stable. This is for a location in Alaska, but for the red, it's like the deposition caused by wildland fire. So it changes dramatically from one year to another. So in order to get very like accurate estimate of contribution of smoke deposition to total deposition, we have to run the model for a long time period and then get statistical and meaningful data. Okay, so another issue is the feedback of smoke. So smoke, you know, is a relative active particle, so it can like reflect or absorb solar radiation. So that will change everything in the atmosphere: temperature, wind, circulation, even precipitation. So because current TDAP model is using CMAC, and CMAC is drawn by a meteorological model like a WRF. So WRF meteorology is the input that doesn't change with time. But for smoke, because the feedback to the atmosphere, the driving itself is changing. So, but how this kind of change can affect smoke deposition simulation? So we have to do some research to understand that. So here is a case study just to get the idea how strong the feedback is and what's the like implication for smoke deposition simulation. So this is for last year in Canada fire. So you see the red dots are fire locations. Then the blue dots are major cities in Canada and the United States, northeastern United States, with heavy pollutions. Basically, it's air quality index exceeding 100. So we run the model for about around 10 days in June, then use the FIN, it's an NCAR developed based on models fire emission products. Yes, this, if you look at just one of the panel, it's, there's a two circulation system over the land area in Canada. It's like an cyclone. So it basically is high pressure, so where temperature is higher, warm, so there's a big fires. Then off sea on the ocean area, actually there is a low pressure system, so it's a payoff system. So you see the smoke plume in the first 3 days, it's basically stay in the land area, but after that there's a transport of smoke plume from Canada to North Big Lake area, also the northeastern United States. Then the smoke plume further went to ocean areas, so get inside of the low pressure system. Okay, so this will reduce because of the absorption and the reflection of smoke particles. So radiation is reduced on the ground. That will reduce the temperature. And so based on the atmospheric dynamics, this will cause the subsiding of air. So basically this there is a movement from top or middle of troposphere to the low troposphere. Then this will actually increase the high pressure. Then there's an increase in smoke plume or PM concentrations. And also there is a change in cloud, but basically cloud and the precipitation is not in the land area because it's dry, which is why fire occurred in that area. But because the transport of smoke to the low pressure system, the cyclone, there's a lot of cloud and precipitation activity over there. So smoke plume actually changes the cloud and the precipitation. It's kind of like this kind of just like a hurricane structure. But overall, you see the yellow color is more than a blue color, which means there's an increase the cloud because the circulation, I mean, the low pressure system is increased, become strong. So basically, this is a 3D dialog structure in the changing circulation. So in the on the left is a high pressure system. We have like air from the top or middle troposphere to the ground. Then on the ground move east to the ocean area. Then up send and move up. So there's a circulation like this. Then because of the secondary circulation, there is more smoke plume transported from the fire location to northeastern United States. So this actually contributes to the heavy air pollution in that area. So then the issue with this, because of the change in the atmosphere, then we maybe cannot use the wolf as an input to a CMAC simulation. Otherwise, the smoke deposition will be underestimated. So but this is a complex issue. We have to do more case study to see if the feedback, the change in circulation is robust, how strong it is. If we have deal with this feedback in the model. Okay, if we consider all these issues with smoke deposition, so basically we have to change it. So the current TDAP is basically a fusion between two things. One is data, the other is modeling. So for both portion, we have to do some change. For the data I mentioned, we have to use more satellite remote sensing data. Then for the modeling, we have to certainly we have to do more evaluation to see how the smoke schemes in the model perform, especially if the feedback and the change in atmosphere is a big issue. Okay, just one more slide. Okay, basically, so we saw the dramatic increase in fire and smoke impact. So this is one of the sources for total deposition. So if we can estimate this smoke deposition, there is a big potential to improve or reduce uncertainty in total deposition estimate. And I just mentioned some changes with current TDAP and MMFO method. But just want to say one more thing about this, because it's a trade-off. Like we can use like coupled WRF and CMAC simulation for smoke deposition simulation. But that will change current like TDAP method, because it's like a decoupled. Also, if you have to couple, that will dramatically increase the computer resources, this kind of things. So we have to consider the trade-off to decide if we have to use coupled or decoupled model to run CMAC. Okay, that's the last slide I have. Yeah. Last slide is to thank you. Yeah.
Great, thank you so much. If you have any questions for Yang, you can find him after the break. So, thanks. Okay, and for our last presentation of the session, we have, okay. Oh, sorry.
Also, I just want to make sure my brother's.
Okay.
Okay. All right, so I'll. Can I move this in some way? Sorry. Okay. Is that good? Great. So I'm gonna present some tools that we've been working on in CLAD, and I'm going to just give you a little background of the kinds of needs that we have, and then talk about the Critical Loads Hub and the Conditions and Trends, which is one of the tools that's within that, and then the class tool for mapping critical loads and exceedance. So the Critical Loads Hub is a portal for all kinds of different critical loads information. It's kind of conceived as to be a sort of one-stop shop for critical loads information. And we realized recently that we had a lot of information that was a little bit hard to keep track of, even for us. And we wanted to make a tool that would make it more accessible to others. And so one of the main things about the Critical Loads Hub is that it's got a guidance portion. So it gives some information about which tool to use for which application, which part of a tool to use if it's a more complex tool, and how to access it. So there's a guidance panel that is Can you see? No. How do I do a pointer thing? Right click on the screen with the here. Anyway, oh, you mean pointer options? Okay. All right, here you go. There it is. So on the right is it step-by-step instructions for how to use the tool that you are looking at. Okay, now I'm going to see if I can get out of here and open up the tool, which is someplace, I hope. Okay, so here we go. So I'm going to show you a little bit, walk you. Yes. Okay. Okay. I thought we practiced this, but I guess we didn't practice it all the way through. Anyway, here is the Critical Loads Hub, and I'm just going to run you through quickly the different portions of it. So there's Critical Loads background information, and there's are things like flyers linked to the CLAD website. There are also videos and links to some webinars, and then there's also some references. So this is the CLAD references that you can see here, and also some EPA references. If we go back to the next section is these tools and reports, and you can access class from here. The retiring critical loads mapper. There are also some summary reports and some air quality reports. I'm going to just show you quickly the conditions and trends report, and I'll point out that when we developed the CL Hub, there wasn't the issue that you couldn't embed one website in another like there is now, and so you need to open it in a new window, but the step-by-step instructions are still over there to the right. And so, oops, that's super cool. Mike, I'm gonna try that again. Oh, there we go. That, I don't know what that first thing was, but so we can select a park, and I'm gonna select Voyagers, which is not so far from here, and we'll select a parameter, and we'll look at sulfur deposition, and then you can see the data. I'm going to try to make it a little bit smaller. Wow, this is like really all messed up, and it was not like this earlier. Isn't that interesting? Anyway, I think you can still see the main point, which is that the condition here for sulfur deposition is fair, and the trend of the deposition is not changing. And so it's based on a bunch of different parameters, aquatic acidification, various things that are doing well, and the herb occurrence, which is rated as poor. So I'm going to just switch over to nitrogen deposition, and you can see not as good, red, bad, and you can see the tree growth and mycorrhizal community is are the poorest ones. Okay, so I can't really see what the time is. Beck, you want to give me a time? To know, I mean, how much time have I used? Okay. Okay, thank you. So the next piece of the Critical Loads Hub is this using critical loads in resource management, and there's a bunch of tools in here. The ones that are grayed out are ones that are not yet ready for us to include, which is to say that there's a lot of development happening. And so the tools that will be included are still in process. But clicking on one of these processes will take you to a page where you can then get to links to do various steps in that process. And so there's also a link for deposition critical loads and deposition data, the National Critical Loads Database, a lichens database, and some deposition maps, which you all know how to get to otherwise. And then finally, there are some EPA documents mostly related to the NOx and SOx review. Okay, so that is our showing of that tool. And then the next tool I want to talk about is the critical loads assessment by site or class. And that tool has as its objective to make maps of critical loads and exceedance more easily accessible, and also to allow the user to select the area of interest. Okay, so now I'm going to get back out of here and go to the class tool. Okay, so it includes sensitive lakes and streams and lichens and trees. And okay, this is a tutorial. It's in development. This whole tool is in development, and this tutorial is the old one. The new one is coming soon. So over here are the nationwide maps, and I'm clicking on the trees and then looking at the summary, and you can see that there are tons of maps there to choose from. So one of the things that we just added to the tool is some settings where you can select various things. And the two things are you can select how you view the exceedance. So in our 2011 paper, we broke it down in the maps down into three colors. So red was for above the critical load, yellow was for right around the critical load, and blue was for below. So we've added a bit of nuance. So in this middle one, there are 3 bins above the critical load. And in the on the right, we added nuance below too. So that kind of aqua color is if the deposition is from 0.5 kilogram to 2 kilograms below the critical load. So that one I think is the best one. But anyway, if you want to see the variation. So I'm going to select that one. And then the second thing that we can choose is for the trees is how we how we aggregate the information when we're looking at the summary of all the trees in a plot. These are based on FIA plots for the trees. So we can look at the minimum critical load. So that's the most protective. It's going to protect all of the trees in the plot. We can look at the 10th percentile, which would protect 90% of the trees in the plot, or we could look at the median, which protects half of the trees in the plot, sort of not necessarily the first choice for most people. Okay, so I'm going to select that. And then now when we look at the maps, it's a little bit more manageable. So I'm going to just show you the growth map. And I want to point out a couple things. Oh, we added this no critical load here. So that's for species which are not sensitive to nitrogen deposition. So these are tolerant species that are not responding to the deposition. So you can see those. And then the other thing is that you can click on an area. We'll see how that's working. Not sure why nothing's working right now. Okay, well, I guess I'm not gonna. Anyway, theoretically, and earlier I clicked on the area and you can see then what the critical load for those points are. And the other thing is that we have a confidence rating embedded into the map. And so you can see that the higher confidence rating is 5 and the lowest is 1. And the 5 are the most saturated colors. The lower the confidence rating, the lighter the color is. Okay, and then I'm going to also show you the exceedance map. I'm going to try clicking again. Yeah, sometimes when you're in presenter mode, like weird things happen and don't work. I'm not really sure why that's not working, but in any case, it also will tell you what the uncertainty is for the point that you're clicking on. So we also have maps for the aquatic and for the lichens. So I'm just gonna show you a different map that we have for the lichens is the predicted decline map. So that gives you, I'm gonna hide the confidence for a second. That gives you information about, given the current deposition, what's the decline in this case, total species richness that you would expect to see at that site. And then one other thing I want to point out is you can overlay, so I just selected the tribal lands. You could overlay the tribal lands on the map, and then you can look at a particular area. Although the way that we had, well, I'll get to that in 1 second. I'm just going to show you the other thing is the deposition maps that are in here as well for the 3-year mean that we used to calculate the exceedance. Okay, so the way that we developed this was that you would be able to select an area and then look specifically at that area. Okay, looking at Voyagers again. And so then it's going to zoom into that area. I'm just going to show you the trees. In the interest of time, I'm selecting nitrogen deposition. I'm looking at the growth critical load, and I'm looking at the summary of all species. And so now I get to the place where I can view the maps over here, and I'm going to look at the exceedance map, and then put the confidence rating in there. You can download the maps, and you can download it in different formats. You can download it as a JPEG, a PNG, a PDF, a TIFF, a GeoTIFF. I'm going to download it as a PDF. Oh, look, that worked. And okay, so I think that's everything that I wanted to show you for the what you can do with the hub. And now I'm just going to pop back here and show you some hot off the press maps that I received at 6:45 this morning. And these show so these are going to be they're not yet in the tool, but they will be added into the tool. So you can see the fraction of trees in exceedance, and you can maybe see the scale there, but basically the darker the maroon is, the higher the percentage of the fraction of the trees that are in exceedance. And you can see that it varies quite a bit by what deposition and whether you're looking at the growth or survival critical loads. The next one is the predicted decline. So this is similar to the one that I showed you for the lichens, where you can see what, given the current deposition, what's the percent predicted decline. The scales are different for survival and for growth, just FYI. And then the last set of maps is about which is the most sensitive species at that plot. And these are in the order of nitrogen growth, nitrogen survival, sulfur growth, sulfur survival. And you can see that while there are some regional patterns, there's quite a bit of variation about which of the trees is most sensitive there. So anyway, I think that gives you kind of an overview of what we've been working on. And thanks especially to Richard with class and various people Richard with the CL Hub and various other people with class.
And we do have a few minutes before the break, if anyone has any questions.
Or suggestions for things they'd like to see in the tool.
This is really interesting. Thank you. I'm excited to explore this further. Is there a way to export data out of the hub right now? Or is it more just a visual interface?
what I just showed you, the mapping tool.
Yes.
So you can download the layers as
Okay.
GeoTIFF
Perfect.
layers. Yeah.
Great. Thank you.
I obviously know the answer to this, but just in talking with our keynote at lunch and kind of talking about sharing tools across agencies, are there going to be opportunities to just like build your own polygons or outside of just pointing and clicking on data in an area you're interested in to get some of these summary statistics of like a city boundary or something like that?
I mean, at this point, we haven't thought about doing that. When we had a regional tool, we were sort of moving in that direction. I'm not really sure what that would entail, but I think it would be interesting to be able to do, and we were able to do this with N-class, like to make a histogram of what's going on in that polygon. So you can sort of see the distribution of exceedance or different species that are present, that kind of thing.
All right, well, thank you. That concludes this session, and we do have a break now.